Excellent. So we will do Q&A, and he's going to talk about tightening your Kubernetes dev loop with mirrored. So welcome, and go ahead and kick off. Yeah. Okay, we clap. Okay, go.
All right. I'm assuming you can hear me okay. Yeah, let me know if there's any issues. Hey, everyone. Thank you for coming to my talk. Great. So it's tightening your Kubernetes dev loop with mirrored, although everybody calls it mirrored. I hope everybody's enjoying the conference so far. Sorry I couldn't be with you in person there, but the Regix team were kind enough to let me do it remotely. So I just wanted to voice my appreciation. A little bit about myself. So my name is Eyal. I'm a software engineer with mostly backend experience. And about a year and a half ago, I co-founded a startup called Metal Bear, where we build open source dev tools for backend engineers. This is the tagline, but we're currently really only building one tool called mirrored, and it's going to be the focus of today's talk. So mirrored lets you do some pretty cool things when you're building Kubernetes apps, and the way we built it is also pretty neat, I think. And it's written in Rust, which always earns us some goodwill from the fringes. So it's worth sticking around. So the problem space that mirrored operates in is the dev loop for developers working on cloud products. So the process of taking new local code all the way to production in the cloud. And I don't think there are a lot of developers, unless they work in really small startups, who are completely happy with how this process works in their organization. It's almost always a source of frustration, and this frustration usually gets worse the bigger the organization is. Because the thing is, when an organization grows, two things happen, right? So the architecture becomes more complex due to more requirements. And two, the organization becomes more reluctant to break its production environment because more users are using the product, right? So it becomes harder to get things into production because it's harder to modify complex products, and you have to be more careful while doing it. So you have sort of a compounded slowness. Now, dev loops come in all shapes and sizes. There are about as many variations as there are tech companies, but still there are some common patterns and archetypes, and this is one of them. So suppose you're a developer making a change to a microservice in your system. So you usually start by coding the change locally, and you do whatever you can to make sure it's tested while still working locally. So this can entail jumping through a lot of hoops, writing unit tests, importing test data or fabricating test data, possibly setting up a local environment with some other microservices. So you have to make a lot of effort trying to test a microservice on your local machine, which is really not the ideal environment to test a component in a distributed system running in the cloud. But then next you open a pull request, which triggers some automated tests in the CI, plus you have to undergo a code review by one or two of the teammates. And this is also a pretty costly step, first of all, because automated tests can take a long time, and they can be flaky, so you might have to run through them a couple times. And code reviews, of course, can take a long time and require other people to take time out of their own schedule. But then what happens next is usually the costliest step, which is deployment to a staging environment, where a staging environment is the closest approximation of production that the organization has. It's usually manually maintained, so pretty fragile, and it's usually shared among multiple developers. So it would have all the microservices running, it would have populated databases, third-party APIs, anything that can be reasonably done to make it a valuable testing environment. But the thing is, you really don't want to fail in that last step. First of all, because you have to go all the way back, make the change locally to fix the problem, undergo code review, automated testing, deployment again, just to get back to where you were. And it's usually shared between multiple developers, maybe teams, maybe the entire organization. So you've potentially just broken the environment for other developers. And of course, the next time you reach staging, some other developer might break it for you. So all this to say, so organizations do what they can to minimize the chances of code failing in staging, which is part of why it's used so late in the dev cycle. But it's a shame because it's such a valuable development asset. As we said, there's a lot of effort put into making it as much like production as possible. But it's underutilized because it's so unwieldy and so fragile. And as you might have guessed, this is where MirrorD comes in. And what MirrorD lets you do is run a local process in the context of an existing cloud environment. So staging for our example. And this can be any local process, no code changes are necessary. And in a nutshell, what MirrorD does is it loads itself into the process, and then it makes it think that it's running in the cloud in real time by redirecting traffic and read-write operations. We'll dive deeper into that a little bit. But this accomplishes several things. First of all, it lets the developer iterate with local code against the cloud quickly and easily. They can make quick changes, test them out without waiting for Docker build, for CI, for deployment. And secondly, it lets them do it without affecting the environment. There's no deployment, and the stable service is still running in the staging environment, still handling requests. So multiple developers can work on the same environment simultaneously without breaking it or affecting each other in really any way. So the point isn't just that MirrorD makes testing and staging easier, but that it makes it so easy that it can be done much earlier in the development cycle. So a shift left on staging. Because you're no longer afraid the test would fail because there are no longer any consequences to it. So this also saves you testing locally in all sorts of stilted ways, like importing test data, setting up local environments, etc. And so now you're testing staging in the first step of your development cycle, and even though you still go through the next steps, you probably only go through them once because you've already tested in staging. So this is all possibly a little bit vague, so we're gonna do a quick demo. And for this demo, we've set up a test cluster in GCP, which includes a few microservices, which you can see on the screen. There's the IP visit counter at the bottom, which is exposed to the internet, and it counts the number of times that an IP has made a request to it and returns it as a response. When it receives a request, it saves the IP of Redis, it queries another microservice for some extra data, and it sends a message to Kafka. And for the purpose of this demo, let's pretend I'm a developer working on the IP visit counter service, and I want to make a change to it and test it out. Now, MirrorD ships as a CLI tool or as a plugin for VS Code or the JetBrains IDEs. So for this demo, we'll use JetBrains Golang. So I'm going to change this to share my screen real quick. Okay. So I'm assuming you're all seeing my screen now. And what MirrorD adds to your IDE is this button, this enable, disable MirrorD button. And what MirrorD does, what this button does when it's enabled is the next time I run my local code, it will run in cloud context. So just to do a little demonstration of what it's like without MirrorD. So we have our cluster in GCP. We have this endpoint, which is exposed to the internet and reaches the IP visit counter. And this is the code for IP visit counter. So we'll enable MirrorD and debug. And now what I get is a dialog showing all of the pods running in my cluster. So I'm going to select the IP visit counter pod. That's the context that I want to run my local process in. A second to start up. All right, there we go. So we hit the first line on main, which is load config. And if we step into the config here, you can see that it retrieves some invalid variables from the cloud. So that's what happens first, and then it tries to read a file from a path that it retrieved from the cloud. So this does not exist on my local machine. We step through. And the file is retrieved from the remote pod as well. It goes through some other setup steps. So it sets up Redis client, Kafka client, all talking with the cloud as well. And let's let it run. And now it's listening to remote requests. So if I hit that endpoint again, I'm going to hit a breakpoint, a local breakpoint on my machine, because the request was mirrored from the remote environment to my local code. So now I can see how my code behaves when it receives these requests, make changes, test them out. And of course, MirrorD offers different modes of configuration, so it doesn't have to mirror traffic. It can also intercept traffic completely, and lots of other things that we won't go into in this demo. So, back to yeah, so that was how MirrorD works. And now that you've seen it in action, let me tell you how it works. First, let me share why we even built MirrorD, right? So even though we recommend that MirrorD be used in staging, originally we wanted it to simply mirror traffic from production. And at the company where my co-founder and I worked before, there was this extremely complex single-tenant production environment, and there'll be 1,001 ways for a code to break that you could never have foreseen before it actually reached production. So version 1 of MirrorD did just that, just mirror sniffing traffic that reaches your remote pod and mirror it to your local process in a way that's completely read-only and could be used safely in production. And that's where the name MirrorD comes from. However, we quickly realized that even though mirrored traffic is nice, it's not enough to test how your code behaves in the cloud, because code behavior is obviously more complex than just handling incoming requests. There are a few other tools that provide kind of a similar experience by networking your machine to the cluster using a VPN or something similar. But this is where MirrorD diverged from these tools. We try to think, how do we completely import the cloud context to the local process without deploying it and without making any changes to the user's machine or code? And the answer was we replace all of its input and output points, and we bring the input in from the cloud and send the output back to the cloud. So I'll start with a quote that I really love from a technical blogger who wrote about us. It summarizes MirrorD pretty well, plus there's a little bit of a brag in there. So some absolute sickos at MirrorD made a system which allows a local process on a developer computer to interact with the network as if it's on another machine in staging. This was achieved by writing an LD preload library that uses the excellent free.gum Rust bindings, which allow hooking arbitrary code in executables by patching functions to insert a trampoline to a wrapper function. So first of all, I think as a software developer, nothing makes you feel you're on the right track more than being called an absolute sicko by another developer. Otherwise, this is a pretty dense quote, so let's unpack it. So MirrorD has two main components. There's the layer, which is injected into the local process with LD preload, as I mentioned before, and the agent which runs in the cloud on the same node as the pod whose context you want to import. So the MirrorD agent is created whenever you start a MirrorD session. That is, you start running or debugging a local process with MirrorD. So the agent is created as a job. It can be automatically cleaned up at the end of execution with pods with some extra capabilities, so then they can access the target pod's file system, network traffic, and environment variables. It can also run on an ephemeral container, which is a relatively new Kubernetes feature, and those make things easier by not requiring some of the higher privileges. So when we start a session, we create the agent, which immediately enters the target pod's network namespace and starts listening in on incoming traffic to the target pod and sending it back to the layer. And then the layer, which I think is the more interesting part, is injected into whatever binary you want to run in the cloud context, using LD preload on Linux or DYLD insert libraries on Mac. And it overrides all of its libc input and output functions for incoming, outgoing traffic, file access, environment variables. We use a library called Frida, which keeps it pretty platform agnostic. So most common frameworks use libc for the syscalls. One pesky outlier is Go. And we actually have a bunch of assembly code just to support it. But it's worth it. So the layer overrides these functions, and then using the agent, it proxies them to the cloud. So the easiest example is reading a file. So for example, when you call read file in JavaScript, it calls open, which returns a file descriptor. Then it calls read on that file descriptor to read the contents of the file. So Mirrd overrides both of these functions. And so when open is called, it's proxied to the agent. The agent opens a remote file, gets a remote file descriptor, and returns that to the layer. And then the layer maps that to a local file descriptor and returns that to the app. And now the app has a local file descriptor that it doesn't know is actually mapped to a remote file. And it tries to read it. So that reaches Mirrd again. Mirrd maps it back to the remote file descriptor, sends it to the agent, and the agent reads the remote file and sends the content back. And the layer, it does the same for DNS, for incoming, outgoing traffic. So there's a lot of mapping back and forth of file descriptors, sockets, etc. And as I mentioned before, Mirrd is written in Rust. We needed a low-level language to write hooks that interface with syscalls and different runtimes. And Rust does a really good job of protecting you from making all sorts of mistakes around things like memory management, which in our case would mean breaking the local user application. And an interesting bonus for Rust, sort of an anecdote, is that it has a pretty hardcore following. Now, Metal Bear is a global and remote company, and whenever we want to grow the team, we use the Rust subreddit. They have a Who's Hiring thread, and we found about half of our team there, and they're all really passionate about Rust and super talented. So, an extra bonus for this choice of technology. So yeah, just to summarize the approach we chose for Mirrd, a nice thing about it is it makes complex flows work seamlessly without any configuration. So for similar tools, what they let you do is route traffic to your local process, but then also mount a remote volume locally to cover file access, import an end file to cover environment variables, and this can get pretty messy. But then let's have a look at how this works with Mirrd, right? So for example, let's take database access. So when Mirrd initializes, as you saw, it loads the remote environment variables into your local process, including things like connection parameters for the database. And then when it tries to read, for example, the key file to access the database, it's going to be read again from the remote file system. And then when it tries to resolve the hostname from the connection parameters that it got from the environment variable, again, it's going to hit the DNS overrides, and they'll do it remotely and get the database's cluster IP from the cluster DNS. So finally, the local process sends a request to the cluster IP, and the outgoing traffic overrides intercept that, and they send the outgoing request out from the remote pods network context instead of from your local process. So you don't even have to expose your database to external IPs, for example. And of course, at the end, it returns the response to the local process. Yeah, so that's about how our approach sort of out of the box solves a lot of complex flows without us having to make any changes and without the user having to configure anything special. Yeah, so that was a little bit about Mirrd. Please try it out. It already has a lot of users and feedbacks are good. And about feedback, come to our Discord. We're always there. We're really happy to help people out with Mirrd or just to chat. If you're interested in the technical part of this talk, We have a blog up on the site where we document our little misadventures with Rust. So you might find that interesting. And I'm personally available on Twitter and would love to have conversations with you about anything. So there's that. Anyway, I hope you enjoyed my talk. Thanks again to the Rejects team for making this possible. And I hope you all enjoy the rest of the conference and that we get to meet in person at future events.
Thank you.